Our second speaker today is Mr. Craig Picetto, who is a Senior Materials and Process Engineer with ES3 in Utah. Craig's current research focuses on eliminating the use of environmentally hazardous materials, such as cadmium and hexavalent chromium, on high-strength steel aircraft components. He earned a bachelor's degree in mechanical engineering from the University of Utah and holds a master's degree in civil and environmental engineering from Utah State University. Craig?
Well, hello everyone. Again, I want to kind of match what Tom the guy said on the CERDRIP and ESC CPU programs. We couldn't have done this project without them. We really appreciate Robin and his group. Also want to thank Tom and the Pollution Prevention Group of the Air Force. And especially I want to thank Dave Frederick and the Landing Gear Division here at Hill Air Force Base. They've been the technical backing of this project. And also we've worked with Boeing and Dips All of America, who supplied the zinc nickel chemical that we've used. Right now we're on slide 30. You can see my agenda. And basically what I want to talk about today is why did we get out of the cadmium business? Two, what did it take to qualify zinc nickel to be used on high-strength steel landing gear components? And three, what did it take to get it approved and implemented on weapon systems? I'm now going to slide 31. Like Tom alluded to, cadmium is a bad actor in the environment. It damages your kidneys and lungs. You get bone embrittlement. It's a known carcinogen of many of your internal organs. It's just bad. Another issue with cadmium, unlike chrome, once chrome's plated, it's trivalent chrome and it stays in place. It's hard to sand off, and it's not a bad issue. Cadmium, on the other hand, if you have any exposed cad, like for instance when you wash landing gear components or aircraft, it'll tend to leach off and go into the groundwater unless you have it contained. Another issue you have is the dust is easily inhaled. One of the issues they've had at Hill Air Force Base, when they strip the paint off the landing gear so they can overhaul it, they put it in a methylene chloride bath. That gets 90% of the paint off. After that, they have to use a plastic media blast to get the rest of it off. And it's very tough to control the dust from that plastic media. So you end up getting cadmium dust throughout the shop. And then additionally, if you have a using activity, if you have the paint, they're trying to touch up the paint or anything, if they sand on, they can liberate cadmium dust there also. Another issue they have in industrial facilities is the cyanide in the plating bath, and the cadmium plating bath. More particularly the rinse waters. You got to be real careful that the cadmium rinse waters don't mix with anything that's acidic. Otherwise, it can liberate cyanide gas, which is a bad actor. And they've had a few issues with that at Hill, but as a whole, they've done a great job monitoring to that and containing it. Next slide. Some other issues, as Tom alluded to, and I'm not going to beat this. OSHA continues to lower the personal exposure limits, and it's just making it more and more difficult for Hill Air Force Base to keep their employees safe, their technicians safe that work around cadmium. And the last bullet there I already talked about is the dust throughout the facility. That's always a challenge to contain. It's not just Hill, it's everywhere. Slide 33. The first thing we did in order to get this project going is that we had to scale up from the lab to a prototype, small production plating tank. And we had to develop the plating procedures. And basically we took, Dipsol had a bulletin on plating zinc nickel, and we took that, and we took the past mill standard 870 with the cadmium plating specification, and we developed a plating spec in order to plate zinc nickel that would work. And we prototyped it all in this small plating tank. And then we had to develop quality assurance parameters. And basically quality assurance is you do corrosion, adhesion, and then hydrogen embrittlement are the big three on quality. The next slide, slide 34, you can see that we developed the plating process. And basically first thing you do is, and we're not really showing it here, but pretty much any plating you got to drip blast it to activate the metal surface. And after that you rinse. And after rinse, you go to zinc nickel plating, then you rinse twice, and then you got to activate the surface again, and we use a 0.1% hydrochloric acid. You activate the surface again, you rinse, and then you go into trichrome conversion coat, and after that you rinse, and then following all that you bake. Currently we bake for 23 hours to make sure you don't have any hydrogen embrittlement. But these tanks were about 325 gallon. We had a zinc nickel. On the left you can see it's a Dipsol IZ17 Plus, or we call it LHE zinc nickel, low hydrogen embrittlement zinc nickel. And then on the right is the conversion coat. And why we started with Dipsol zinc nickel, I want to back up a little bit, is they were using zinc nickel in the automotive industry for years, and the type of zinc nickel they're using has leveling compounds in it, and the problem with those leveling compounds, they kind of seal the plating, so it makes it difficult to bake out hydrogen. And so we worked with Dipsol, and we came out with a different zinc nickel where we remove the brighteners or the leveling compounds, and we have a formulation that works well on high strength steel. And now the required testing, as you can see on slide 34, as follows. We did an adhesion testing per ASTM B571, and basically what it entailed, you take coupons and you check the adhesion of the zinc nickel on the steel surface substrate itself, and then there's additional testing, more or less the paint adhesion. How well does the paint primer adhere to the zinc nickel plating? Next we did is hydrogen embrittlement testing per ASTM F519, re-embrittlement testing per ASTM 519, and the Air Force drawing 2525019. There's a couple of different re-embrittlement tests there. And then we did some testing that's really not required, but it gave us a great data point that on doing liquid and solid metal embrittlement testing of the zinc nickel and cadmium. And actually, zinc nickel performs better than cadmium. You can actually go over 500 degrees. You don't have to worry about liquid metal embrittlement with zinc nickel. So that's really makes cadmium better in like break areas where you have high temperatures typically. We also did fatigue testing, and next slide 36. We did corrosion testing, more or less in a booth, ASTM B117 salt fog corrosion, and basically the main requirement for passing all these tests, it had to do as well or better than cadmium, which zinc nickel has done in all of them. We did SO2 corrosion per ASTM G85. We did that more or less to help the Navy. They require this testing. It's not required by the Air Force. And again, zinc nickel did as well as cadmium. Now, neither of them did really well in the SO2 corrosion, but it's a really aggressive test. And then the last thing is, and Tom talked about this a little bit, you got to, once you have this plating in the field, how are you going to repair it if it gets nicked up in the shop during overhaul, or if it's out in the field? And so we developed a brush plating repair for it, and we did corrosion, we did adhesion and hydrogen embrittlement testing on this brush plating, and it passed all that. So it took us a couple of years to complete all this testing. There was bumps in the roads we had to work with. We worked with AFRL and Boeing Boeing military out of St. Louis was instrumental in this, and Dipsol. It took several years to get this qualification completed, but we made it through the gauntlet. And after that, the next challenge, then, okay, what do you do to implement it? And one of the things we did early on is we needed to scale up to full-size production tanks so we could actually plate full-size gear. And again, Tom Nay guys and the STCP were influential and helped us to get funding to implement this line at Hill Air Force Base. It's a 3,200-gallon line. You can plate the largest landing gear in the Air Force, a C5 bogey plated in this plating line. And the tanks are 10 feet deep, 10 feet long, and about 4.5 feet wide. And it's a spectacular facility, and it's been operational since May of 2013. Going on to the next slide, slide 38. Okay, once you have a plating line in there, you've got to make sure you have good conformal anodes. And one of the softwares we developed here at ES3 is called Venus, and it's a plating simulation software. And one of the challenges you have with zinc nickel over CAD is zinc nickel, and I'm going to show you in a slide here in a minute, is kind of a purplish, and it's not translucent. You can't see down into it. So unlike CAD, where you can hang a component on it and then put the component in the solution and take a brush plate and try to plate in recesses and lugs. You can't do that with zinc nickel because you can't see down in the solution. And so you need a software to help you determine where you can put conformal anodes, and that's what I'm showing. On this, we have a torque arm on the left, and this is when we simulated in the blue areas where you're not getting enough plating. And the right is if you have conformal anodes. And the next slide, slide 38, I'm going to show you what it looks like. So you can see on the left-hand side, you see a torque arm, and we've more or less simulated. You need a conformal anode right in. I'm going to pick up the pointer now, but you need a conformal in these recessed areas here in the channels, you might call it, and also where the lugs are. And you can see the little red conformal anodes. And then on the right over here is actually the plating fixture. You can see the conformal anodes right in the recessed areas that are made of nickel and in the lug faces. And then you see this fixture around it. You need that fixture to hold all the conformal anodes in place and also hold the part. Next slide is actually showing a part being plated in the conformal anode. In the far left, as you can see, the purple plating bath, and you can't see in it. So you really need fixtures to hold your part and to do a good job in plating. The next picture over is kind of center left. You can actually, it's a drag brace, and you can see the nickel conformal anode. I'm going to point this out, kind of going up the middle of this fixture right here. Right there you can see the nickel, and then there's a nickel conformal anode right in the lugs to make sure you get good uniform plating where you get current density drops in those areas. And then on the two pictures on the left are actually after it's plated, good uniform coating. It's kind of a bluish color. After you bake zinc nickel, it goes kind of a purplish brown color. But this is a great coating on this drag brace here, and it's all due because you designed a conformal anode, and it's important, and it's really what helps the process if you have a simulating software like Venus to making sure that you're putting your conformal anodes in the right place. Next thing we did was we did a field corrosion. We ensure that it's going to do well in the field before we put it on landing gear and on aircraft. Basically, we have it in 3 sites, three field corrosion sites: El Segundo, California; Whidbey Island, Washington, which is about 60, 70 miles north of Seattle at a Naval Air Station, and Kennedy Space Center. And we were 3 to 4 years we had these components out in these sites. And I'm going to show you in the next slide. Slide 42 is El Segundo. It's the most corrosive site. And the reason why, it has a refinery right there, and it's literally 100 feet from the beach. Just south of it's Manhattan Beach, where all the Missy May and all the ball tournaments are held, just right there. And Boeing has a little corrosion facility inside this Chevron refinery where we place these components. And here I really want to make a foot stopper for conformal anodes. On the left is CAD plated, on the right is zinc nickel. They both, you can see right in the web area, the CAD corroded worse than the zinc nickel, and so you can say zinc nickel did a little bit better. But the big thing I want you to understand, when these were plated, we didn't use conformal anodes. So I'm going to get the pointer right here in this web area. There had only been about 1/10,000 plated here, whereas on the ribs and the rest of the component it was probably 5/10,000. So it's 5 times as thick, and it shows if you don't use conformal anodes, you're not in a good uniform plating. And this is effect in the field. So this is where rubber hits the road in a kind of an aggressive environment. Next slide, slide 43. This is some rotational gears. We have Whidbey Island. This is a less corrosive site that we had, partly because of lower temperatures and you don't have SO2 or NO2 coming out of the refinery. And we got a little corrosion as a whole, but again, zinc nickel did as well as CAD. Next slide, slide 44. This is Kennedy Space Center. This was our next most corrosive environment. It's warm there, 100 feet from the ocean. Oh, the slide changed. Let me forward it again. But rotational gears again, and both zinc nickel and CAD did relatively well there. Next slide, slide 45. We did performance tracking, and basically we took 2 to 3 components on several weapon systems, aircraft, We plated them, we painted them, and then we put them on landing gear and put them in the field. Here I'm just going to go, we did a total of 4 sites, but I'm only going to show 2 sites. One is in North Carolina, the other's in Hawaii. And believe it or not, Hawaii is a very corrosive site. So slide 46. Well, here is F-16 aircraft, and we plated the rotational collar, the drag brace, and the tension strut. Slide 47. And I don't have time in this briefing to show you all the components, but one thing I want to show you, this rotational collar. On the left is zinc nickel, and it just looks fantastic after a year and a half in the field. On the right, we have cadmium, and I want up and I'm going to get the pointer again. I just want to point this out. Up in this area, you can see where the CAD kind of corroded and rubbed off, and so it didn't stay on as well. And in this area is grease, but the grease absorbs water. And I was an engineer on the F-16 for a number of years, and we'd always get a lot of corrosion in here. And this is part of the reason why. Next slide is slide 48, and this is a C-130. We again, we zinc nickel plated and paint and primed on the main landing gear torque struts for the C-130. Next slide, slide 49. This is actually the CAD. On the left-hand side, we had CAD. On the right-hand side, we had zinc nickel of the aircraft. And this is Dave Frederick. He was great throughout this whole time doing this project. Dave was instrumental in making this work. You can see there's no red rust. Everything, this landing gear been out 2 years, and this is in Hickam Air Force, or no, excuse me, Barbers Point, Hawaii. It's a Naval Air Station or Coast Guard station, and it looks great after 2 years. And then the zinc nickel, slide 50, is and zinc nickel, it looks just as good as cadmium, are both performing very well in the field. Next slide, slide 51 is conclusions. In conclusion, zinc nickel passed all the qualification testing that we had. It did, all our beach corrosion sites, field corrosion sites, and also in the performance tracking plan. It did great, and it got approved by Dave's group, his engineering source approval activity for landing gear. It's been approved by landing gear group to go on aircraft. It's flying. Zinc nickel components are flying now. There's over 1,500 components out in the fleet right now that have been plated, and it's just done really well. And that's pretty much all I have to say. I don't know. And one other foot stomper I'll hit again. You have to use conformal anodes to get a good uniform plating. And I don't care if it's cadmium or zinc nickel. If you want good plating, you need conformal anodes, especially for zinc nickel. I think that's all I have.
Okay. Thank you very much, Craig. And I would like again to remind the audience, if you have any questions for Craig, please type them into the chat box in the lower left-hand portion of your screen. We have received a number of questions, Craig. The first is about the software. Is the software that you referred to for designing the conformal anodes publicly available?
Right now we develop the software internally, the ES3, but if somebody would like to use it, I'm sure we'd be willing to license it for them for their use. I mean, we can open up that discussion.
Okay, great. And how many landing gear components have been plated and are currently on Air Force aircraft?
There's over 1,500 components have been plated and are on aircraft right now flying for the U.S. Air Force. Wow.
And how often do you need to analyze the plating bath in order to maintain uniform compositions?
They've had since May of 2013, they've had that plating line up at Hill Air Force Base, and they do their monthly tests, hydrogen embrittlement, corrosion, like I was indicating, adhesion they do on a monthly, and then they have chemists up there that come and measure the solution and do analytical on it, and they do their ads as required. It's not much worse than cadmium to keep it in compliance and going.
Okay, great. We have received a couple of questions about the zinc nickel composition. what are the zinc-nickel ratios, for example, at high and low current density locations? And then another question was about the nickel content by weight in the plating.
Okay. Those are some interesting questions. When we first started the project, we had zinc nickel. We're running between 12 and 18%, and as far as I'm concerned, it can be between there, and it does fine. But what we found is between 12 and 15% is the sweet spot. And how we've measured it, we've used XRF to determine the quantities of the nickel in it, and if basically if you're around between 12 to 15%, you get a little better corrosion, and it does just a little bit better in fatigue. Will it pass at 18% in fatigue? It will. It just does a little bit better, and I don't want to think people, oh, it's 18%, it's bad. Not by any means. It's just if you can hit the sweet spot, and that's what we've done with. We have an Air Force specification, and it's Air Force drawing 201027 456, and in that specification, we've tweaked the chemistry to be that 12 to 15%, and also what makes good about that, it matches the Dipsol bulletin, and also Boeing aircraft spec 5680. And I've never really done it by weight, so I'm not sure. We've just done XRF analysis to determine what percentage is zinc nickel, and so that I can't really answer the by weight question.
Okay, thank you. Are there any applications for which zinc nickel is not appropriate?
Boy, that's a good question. It can be used pretty much anywhere CAD is. I know basically what Tom said, each weapon system or group has to go through and go through it and make sure it's safe for their weapon system. I know some issues they're looking at right now. We're looking at conductivity on connectors. We're working with the ICBM group, and they have some conductivity issues, and we're doing some testing to try to more or less make sure it's safe to be used in those areas, and that's it. So.
Okay. And what is the anode material?
The anode material is nickel 200, and you can, if you want, you could take steel and plate it with nickel. But if you get any nicks in that steel, it'll contaminate the nickel plating. It'll contaminate your tank. So all the fixtures we make for the Air Force are solid nickel 200, and it's our belief that's the way to go. And truthfully, that's what a lot of industry's doing too. They don't want to risk that getting a steel-plated conformal anode that's been plated with nickel. If it nicks itself, it'll start contaminating the nickel plating bath.
Okay. And one final question for you. Is a military standard going to be developed for the LHE zinc nickel plating?
It is currently being developed. Dave Frederick, he's the TPOC on this project, he's submitted a mill standard to the Air Force. It's a slow process. I won't be surprised the Navy beats him, but both the Navy and the Air Force are trying to push forward a mill spec similar to mill specification, similar to mill standard 870 they have for cadmium. And I think it'd be great. I want everybody to understand too, if you're following Air Force drawing, you're right there with BAC 5680 and it's and the Dipsol plating spec also. We did this on purpose. We want the world to use it. Steve Gatos, who works for Boeing, he bottom line said, we could keep pushing CAD, but we need to get better. We need to have something safer for people, and Boeing as a whole has been very good about trying to get this out also.
Wonderful. Thank you so much, Craig, for the presentation and for answering questions. And we will have Craig back at the end of the webinar for a few additional questions. Now it's my pleasure to introduce Randy Straw, who is a product support specialist assigned to the Air Force Lifecycle Management Center Product Support Engineering Division. Randy performs technical and program management activities in the areas of aerospace-related materials and processes and pollution prevention research, development, testing, and evaluation. He retired from the U.S. Air Force with over 19 years of aircraft maintenance experience specializing in aircraft and ground support equipment, corrosion control, and protective coatings. Randy has a bachelor's degree in logistics management from Park University. Randy?
Thank you. And I'm going to start off by echoing Tom and Craig's appreciation to ESTCP for supporting this project. Again, with ESTCP, I think most of you know they are competitive projects. We put together plans, we go to ESTCP, and they down select, and ultimately they thought some of these projects were worthy of funding, so we definitely appreciate all their support and help along the way. So we're going to start on slide 55 with the agenda. It's the typical, we're going to go over the project goal, an overview of the technology we're going to be talking about with the brush plating station, as well as the solution that goes along with it. The benefits, the testing, a process study, we're going to get into that a little bit about making sure that the equipment is usable. The sustainability analysis, a little bit about where we are, and then our conclusions and where we're going forward. So we can go to slide 56. So this project, we have two goals. The first, we're looking at a commercially available, commercial off-the-shelf brush plating station. I think most people are familiar with brush plating. Right now the equipment is pretty low tech, but this is a computerized, self-contained brush plating station. It actually recovers the solution at the point of use. It's got a lot of benefits, and along with that, we are looking at the manufacturer's commercially available zinc nickel solution as well as an alternative to the cadmium. We're not out trying to just arbitrarily replace the current solution, but competition in the government's eyes is always better. So we can go to slide 57. So like I said, it's a computer-controlled, self-contained brush plating station. There's a picture of it on the right. If you look in that picture, on the right side of the picture, there's a computer screen. It's a touch screen. In this case, the operator goes up, they enter information, and this is also tracking who the operator is, what the conditions were. So it provides us a little bit more history than paper logs and those type of things. One of the things that we like about it is right now when the operators go out, this thing, if the operator is going to go out and do a small area, they've got to do manual calculations. They put in the size of the area they're going to plate and the thickness, and then they have to get out the pencil and paper and do the calculations for the current as well as the time. With this station, the operator will go up and enter in the size of the area and tell it how thick it wants. Then the computer does the calculations. The operator hits the on button or the go button and just starts plating, and then whenever it's reached enough time, the unit will automatically shut off. So we think there's a lot more control on that. Look in the center of that, the three stack there. The top is the electrical power supply, and then the next two are the pumps. There's one for the activation solution or the surface preparation solution, and then the other is actually for the plating solution. So those go off, and on the right side, it's a little bit hard to see, but there are the containers there. There are brush plating wands for each one of these stations. So the operator, when you go out and do the activation part, you get the surface ready. You don't have to purge the machine and clean it out. Then you just set it off to the side, and then you pick up the brush plating wand and press on. So it's also got the step-by-step operating instructions are on the screen there for the operator to use. And like I said, with the dual tank solution, what we like is you don't have to stop in between the surface activation and the plating process. The machine is also keeping track of the amp hours and the time on the solutions, and instead of, again, going back to paper logs, it'll keep track of the time on the solution, and then it will tell the operators when it's time to change it out or when it's depleted. So we'll go to slide 58. So these are the typical benefits from it. Again, I think a lot of folks are familiar with the brush plating operations. The current process, it's an open process. The operator takes the plating stylus. There's an absorbent material on the end. You dip it in the solution, and then you start rubbing it around on the area you're plating. As you can imagine, if you're working on a bench top, it's not bad. But if you start working on vertical surfaces or even worse, start working on overhead surfaces, you've got this solution just kind of running everywhere. It's dripping down, it's running down surfaces. So we have problems with that. The uncontrolled plating conditions, again, we're relying on the operator to do a lot of calculations, and they can overplate, they can underplate. They're sitting there with a stopwatch or just basically looking at their watch, trying to figure out the times. We have, because it is an open plating process, we have to do a lot of damming with absorbent materials. We know the solution is going to drip, it's going to run, it's going to get everywhere, so we're trying to do the best we can to keep it from getting everywhere. So we spend a lot of time making sure that we clean it all up. So we have a lot of hazardous waste from it. It's not as much the brush plating solution that we're getting rid of as much as it is all the containment materials, the absorbent materials, the protective equipment. And then like Tom said, we do have a lot of the health risks, both the occupational health as well as the environmental impact of this. So with the dolly stick station, it's a dripless plating station. It's a closed process. So as the solution is being put out onto the surface, it's also being recovered. There's a vacuum system that recovers and recycles the material so that we can go ahead and reuse it. We know that we're going to extend the life of solution because we're keeping a lot more accurate count of the amp hours and those kind of things. And on the occupational safety and health side, the zinc nickel has a lot lower occupational safety and health risk, and we require a lot less PPE. So we can go to slide 59. Okay, I apologize for that slight interruption there. But on the screening testing, because this is an ESTCP project, we developed a joint team whenever we went in for the proposal. So we've got the Army and the Navy on board with this, as well as the Air Force. So we went through and come up with our screening tests. We're identifying the materials we're testing, the substrates, as well as the type of tests we're going to run on it. So here we're doing the testing on 1008 and 4130 steel. The 4130 is our version of the high-strength steel that we're using for this. We're comparing the brush plating to traditional brush-plated CAD and the zinc nickels that are currently in use in the Air Force and some of the other depots. And then we're also looking at the scenarios, the fully brush-plated. As part of this, we want to make sure that the zinc nickel solution that we're using is cross-compatible, so we're going to use it to repair CAD, things that have previously been CAD plated. But also in the event if we use something with zinc nickel, can we brush plate it with CAD or the other zinc nickels? So we're looking to make sure that these things are cross-compatible. So if we go to slide 60, please. So in our screening testing, this was the first round of testing we're doing, and we were doing the typical thickness, appearance, bend adhesion, the composition. We're checking the zinc and nickel composition, the percentages, and the salt spray, putting it in the salt fog chamber. So go to slide 61, please. So the initial results, the thickness, it all passed. Basically what we were doing was measuring. There are some specs out there on the zinc nickel and the CAD plating, but we were also going with the manufacturer's recommendation on the thickness of the Zinadol or the dolly stick brush plating, the one we're testing now. Visual appearance, everything passed, as well as the bend adhesion. Basically, we plate our samples and then we bend them till they break, and we're looking to see is the coating flaking or spalling off. So on the bottom, you can see one of the visuals for the zinc nickel with the conversion coating. Now with this, we are testing with the hexavalent chrome conversion coating. The manufacturer is working on a trivalent chrome, and eventually we would like to get to a non-chrome conversion coating on this. Just to, we don't want to keep introducing the hex chrome, get rid of the CAD, but to have the problems we have along with it. So we can go to slide 62, please. Again, our composition results. These were done, if you look at the qualified zinc nickel solution, the columns on the left were averaging a little over 7% nickel by weight and a little over 92% zinc by weight. With the Dolic or the Zinadol zinc nickel solution, we're up to almost 11% by weight nickel and right at 89% zinc. Again, these are within the manufacturer's specification or their recommendations on their solution. So we go to slide 63, please. Salt spray resistance, we've got this done. The goal is no white rust or no white corrosion products after 96 hours of exposure. You can see both the traditional brush-plated CAD as well as the traditional zinc nickel brush plating and the Zinadol zinc nickel solution all past 96 hours. Go to slide 64, please. We're also looking at the red rust over the steels. As you can see, the traditional brush-plated CAD, everything passed. With the traditional zinc nickel as well as the Zinadol, we had a lot of the passes were on the scribed, or the unscribed, I'm sorry. The scribed failures, the original specification calls for 250 hours. It passed the 250 hours, but we were trying to find out where the failure point is. So in our test plan, we had said, let's run them out to 500 hours. So all the failures were over the 250, but less than the 500-hour timeline there. So go to slide 65, please. So the process study was our way of looking to say, okay, we want to make sure that the equipment is usable and it's not as much operator dependent as the current process. So we took several plating operators and we had them plate a variety of samples, and rather than doing things like we're going to do our thickness panels and we're going to plate all those at once, we had the operators, we switched out operators maybe every panel or every other panel, and then we pulled random samples out. So we were able to go through and look at things like thickness, appearance, the coating composition, and what we found was that it didn't make any difference which operator plated it. We were getting good results. Some of the other concerns were the size of the area we were plating. So if we're plating larger areas or smaller areas, are we going to see differences in the composition or the thickness or the other important factors? And we didn't see anything there. And then as the solutions are being recycled, we were wanting to verify that as the solutions are being reused, that we're not losing the ability to plate properly. So after the end result of all our process study, we found out that it really didn't make any difference as far as which operator was plating which panel, what the sizes were, or even as we were using the solutions. Now, we haven't run them completely to failure yet as far as where we've basically completely depleted the solutions. But again, going back to the machine keeping track of everything, it will tell us when it's time to change the solutions out. So can we go to slide 66, please? And this is just an example of, in our study there with the mean thickness, you can see we did 142 specimens with the Zinadol solution, and then compared to the traditional zinc nickel and the CAD brush plating. What we found was, even though the thickness, it's a little over 11 microns, almost 12 microns, it's thinner than the other two solutions, but again, it's within the manufacturer's recommendation on the thickness. But you can see we get much more consistent and repeatable thickness irregardless of who the operator is. So if we can go to slide 67, please. The sustainability analysis, it's a lot of folks call it, we start off with a cost-benefit analysis. And when we did the straight cost-benefit analysis, because of the initial purchase price of the dolly stick unit compared to the typical brush plating setup, if you're looking at just that, it turns out that the current brush plating process in the long run is it's probably more economical. But with the sustainability analysis, what we did was looked at things like the occupational exposure, the environmental benefit, or the environmental impact from it. So again, we were taking a look at all these things, and whenever we rolled it all up, over the lifespan of the units, the brush plating station is going to be slightly more expensive than the current brush plating process, but we have, on the flip side, we've eliminated or greatly reduced the exposure of our workers to these hazardous environments. So you go to slide 68, please. So where we're at now, what we have upcoming, we did have a slight break. We had to send the unit off for some repair and maintenance, but we've got it back and we're up and running again. So we are going to do outdoor exposure, similar to what Craig said, where they put samples out on the beach at different places. We're plating a bunch of samples. We're going to put them on the beach down at Kennedy Space Center. We're going to track them, and we're going to compare them against the current brush-plated CAD and the current brush-plated zinc nickel. Our repair scenario, again, we're looking at if we take something that is already plated, because again, with brush plating, you're looking to repair a previously plated surface. Not necessarily, we're not out to brush plate a whole part. So we're looking, again, we're going to go back through the thickness and appearance, the composition, the corrosion testing, the adhesion testing. The paint adhesion, we want to make sure that we can get the paint to stick to it. And then hydrogen embrittlement. And along that lines, CERTUP and ESTCP have also given us some additional funding for this project, and we've got Boeing and one of their partners, Ibeca, just recently on contract to do some further investigation into the whole hydrogen embrittlement phenomena, particularly as it relates to what we're doing with the brush plating here. Again, these things are supposed to be low hydrogen embrittlement. We can't get you can't put a whole airplane or a whole part in an oven. If you go out to brush plate a bushing on an airplane, you can't put it in an oven and bake it. So we have the hydrogen embrittlement thing is something we have to keep an eye on. With the demonstration plan with ESTCP, they do require this, and it's typically a 6-month to a year-long demonstration of the technology. Currently, everything we've done has been in a controlled environment, more of a laboratory type environment. We are working with the Navy down at Jacksonville, Florida, and our plan is to send them the unit and let the depot platers down there work with it. And what we want to find out is their honest opinion of, is the equipment worth getting? How does it work? How does it hold up? How does it compare to their current technologies? So we hope to get all that worked out and get the field demonstration started sometime within the next couple of months. And then we'll wrap the project up after that. So we can go to slide 69, please. So again, what we're seeing is with the dolly stick unit, with it being dripless, we think there's a lot of environmental and occupational health benefits. We know that we've already shown that we have better process controls than the traditional process, and we think that this nickel solution also has the potential to be qualified for use on high-strength steels and get it out there. And I think that is the last slide that I have.
Wonderful. Thank you so much, Randy. And if the audience has any other additional questions for Randy, please do submit them at this time. We have received a number of questions. First question is, have provisions been made to apply this to stainless steels?
Not at this point. We've got, like I said, we're using the typical steels that we have.
Okay.
But that is something we can take into consideration.
Okay. And does each repair need to be certified by a program?
Again, we will work back, as Tom talked about, with the airworthiness process that the Air Force has put into place. Our plan is, when the time comes, we will take this forward, and we work back through the subject matter experts, and we go to the Airworthiness Board, and the ultimate goal is to get a no airworthiness impact determination. But then, like all the other processes, once we turn it over, the chief engineer is going to have to, in some form or another, authorize it for use on the aircraft. But once it's in use out there, then they can put in any limitations or restrictions or no restrictions at all.
Right. Okay. Is the reuse of the plating solution acceptable, permittable, and per the plating specifications?
The permittable part, I'm not sure if that was considered an environmental issue, or if that is just a permissible for the use of the technology on the aircraft. There is no specification for this piece of equipment at this point. But again, as part of the airworthiness process, we will come up with a process specification for it. And it will also include the reuse of the solutions.
Okay, thank you. How does the process time for the dripless station compare to the current brush plating technology?
What we're finding is the actual brush plating time is comparable as far as the amount of the current draw and the time. Where the total process time, where the benefits are going to come in, is the amount of masking and barrier material that we have to put down prior to actually doing the plating, and then all the cleanup and disposal that comes afterward, along with allowing the operator time to put on their protective equipment and to take it off. So we think that the process time is actually going to be shorter.
Okay, thank you. How portable is the dripless unit?
Right now, the unit that was shown in the picture there weighs about 110 pounds, and that is probably the top of the line, the biggest unit they have. It is on a mobile cart. It can be rolled out to the airplane. Requires 110 volt electrical supply and compressed air. But the manufacturer has taken it out and used it on top of airplanes. So the hoses, you can put the unit on the ground. The solution hose and the vacuum hose, they've run it out to at least 20 feet at this point. We have not seen if it will go beyond that. But I do know, I've been told it's on the F-35. They can take the unit out and set it off to the side of the airplane and be able to get up and do whatever they need to do on the airplane with it.
Okay, thank you. And what is the cost of the dolly stick unit?
The cost ranges between $50,000 and $120,000. The unit shown there was $120,000, but that was the first one of the machines in that configuration that they had put together. So once they get into production, the costs may come down some, but at this point I really don't know.
Okay. Can you plate IDs with the dolly stick?
They can do some. Some of it is going to be designing the wands or the brush plating stylus that goes inside. I don't know. I don't think that they have gone on small IDs yet, but it's something that we could get with the manufacturer and see what the smallest possible sizes that they could do are.
Okay, great. Can you comment on the conformal anode capabilities of the dripless system?
There are none required.
Okay. And you referred to galvanic corrosion between materials. Which materials are you referring to with respect to that?
Some of the concern is if we have fasteners, and that's where we were looking at for the galvanic, is if we are going out and touching up. And the typical panels that we have are aluminum panels or steel panels with either aluminum or steel or titanium fasteners run through them. And we want to make sure that we don't set up a galvanic couple between the base metals and the fasteners or the different metals that are combined together. So at this point, they've been the aluminums and steels, and then steel or aluminum or titanium fasteners.
Okay. Can you comment on why the brush plating nickel content, around 11% in your, as presented in your presentation, is smaller than the range of 12 to 15% mentioned by the previous speaker, Craig?
Right. That was with Craig. He was talking about a tank-plated process. And with the brush-plated process, you are going to see differences in probably a smaller nickel content. If we look at the current CIFCO brush plating material that's authorized out there, what we've seen is the nickel content on that is closer to 7%. And they both seem to be doing quite well in the corrosion testing, or comparable in the corrosion testing.
Okay. And going back to the cost of the system, what is the cost difference between the dolly stick and the traditional setup?
I haven't priced a traditional brush-plated setup, but I know they are not very expensive. But long-term, because they are basically an uncontained, uncontrolled system, you can buy a relatively cheap unit, but you are going to pay a lot more for barrier material, cleanup, and everything else in the long run.
Okay, thank you. And we have time for about one or two more questions. What is the largest area that has been plated with this process?
I don't know what the manufacturer has plated. All of our samples are typically the 3x6 samples that we've been doing in the lab setup.
Okay. Thank you very much. And at this time, we would like to bring back both Tom and Craig for some additional questions. The first question, Tom, was specifically for you. So we'll start with you. Has the Air Force settled on a specific zinc nickel coating that will replace cadmium on fasteners across all airframes? And if so, what is the status of that implementation for the fasteners?
Okay, this is Tom. I'm not sure we've established what the final formulation is. Randy, do you know off the top of your head is what the final for the CAD fasteners?
No, I believe that's still in work.
Right. We're narrowing it down, but it's not finalized yet.
Hey, Tom, this is Craig
Yep.
Cassetto. I know
Yeah,
ES3, we have a Phase 3 SIBR, and we're working that with in our Georgia office, but it's similar to the chemistry for the landing gear, so it's very close.
Okay. Thank you.
Okay, thank you. Can you describe how these alternative plating or brush plating technologies can or will get implemented at other DoD or OEM facilities? Tom, we'll start with you, and if you want to defer to Craig or Randy, just let me know.
Okay. Well, one of the key elements that we leverage the CERTIP symposiums for and these webinars is to get the information out. I know the Army and Navy have been following what we've been doing in this area, and their transition path and their qualification path will leverage ours, but can't really specifically speak to how the others in the DoD will also go forward.
This is Craig Cassetto. I know as far as high-strength steel, the companies, Boeing Commercial and both military have approved LHC zinc nickel for use on their high-strength steel. It's in BAC 5680 Boeing aircraft specification. I know here a couple of months ago, Safran approved it for use. I know UTAS, who makes a lot of landing gear, is currently looking at it and getting really close to approve it. Haru DevTech and other landing gear companies have approved zinc nickel, this IZC17 dipsol for use. And then I know, like Tom was saying, that the Navy has a Phase 2 SIBR and on the looking at zinc nickel also, and they're getting pretty close to approving it.
Right, and this is Randy. On the brush plating side, so whenever we have these projects, we do bring in the Army and the Navy as team members, and they put their technical requirements in. And in our case, whenever we're looking at the demonstration site, we are looking to ship the unit once we're done plating our samples is to ship our unit down to the Navy Depot, Jacksonville, Florida, and working with the NAVAIR point of contact down there and let them do the demonstration validation. So we're going to be providing them a piece of equipment that they can evaluate, and then along with all the results of all the testing that we've done. And same thing with the Army, we provide all the results in publicly released reports. Also, whenever we go to things like the CERTA BSTCP symposium that Robin mentioned earlier, and through other various publicly released social media type things, we get the word out as much as we can.
Wonderful. Thank you all so much. The next question will start with Craig. How much longer do you anticipate that the European REACH organization and EPA will allow cadmium to be used in aerospace applications?
You know, I believe once zinc nickel gets out there that there's a good substitute. So this is just my speculation that they're really going to put the screws to cadmium because there's a replacement, it works, and in zinc nickel it's a drop-in, and I don't. It's in my belief once it's been approved by a lot of the manufacturers, it's just you know, a few years before they really put the screws to us and tell us, hey, there's something out there. Please use this instead, and we'll no longer accept cadmium. But it's just my opinion.
Tom or Randy, any additional comments?
I tend to second what Craig is saying. Once that there are well-defined approved processes or approved alternatives, then it could be that they don't have an outright ban. I think in some cases what we see are the exposure levels drop lower and lower and lower, and it gets harder and harder to meet. And it may not be an outright ban as much as it is just either an economic or a physical practicality of meeting the requirements. But on the other side, we do have, there's always the possibility of either military exemptions or national defense requirements. I'd hate to get into the idea that the environmental folks are going to tell us how long our airplanes can stay around.
Right. And this is Tom, and I tend to agree. I've talked with several folks that support the regulatory committees, both stateside here and international. Nobody wants to force us, the aerospace community or any other community, into a high-risk situation where we would endanger, consumers or travelers on airspace or any military members with working on a weapon system or flying in a military airplane. So, just to foot stomp what Craig and Randy just said, as soon as that, solution starts to take foothold, there'll be much, much more pressure to eliminate it. And legacy systems, as they come in for overhaul and rework, will start to incorporate the new technology like zinc nickel as well.
Thank you. Is there or should there be a concern with substituting a nickel alloy for cadmium? Is nickel the next to be regulated?
Well, nickel's already listed as a carcinogen by the state of California, but it's...
Yeah, I'll just say that, there's been, periods in time where regulators have looked at that, but I have yet to see any clear path to regulate nickel farther than what currently is.
Yep.
Okay.
Yeah, I tend to agree with you.
Okay, thank you. The next question is for Craig. Have any other commercial aerospace companies approved LHE zinc nickel plating on high-strength steel aircraft components?
Yes, Boeing Commercial, both Boeing Commercial and Boeing Military has approved zinc nickel for use. It's in their Boeing aircraft specification 5680. It's in there currently, and it's similar to the Air Force drawing on how to plate. Also, Safran has approved it for use. Haru DevTech, who makes landing gears, approved it, and there's others that have done so also. So it's really starting to take hold. I know Boeing's put it in their requirements for their new aircraft. Their legacy systems not so much, but just a big cost in redoing all their drawings. But moving forward, they're converting all their aircraft to zinc nickel in lieu of CAD. So it's starting to go, and we're getting a lot more questions, more companies calling us and asking us for places where they can get zinc nickel plating. We at ES3 also have a zinc nickel plating line in our Georgia facility, and we're able to do it also.
Okay, thank you very much. We have time for one last question for our three speakers today, and we'll start with Tom. What additional research or engineering needs must be accomplished to better support and expand the use of cadmium replacement technologies?
Well, I think as the technology starts to get in use more, I think, and gets expanded into other components and other weapon systems, I think there's going to be a need to further understand the actual mechanisms of zinc nickel, especially when you start putting it into a system of materials, when you start to add specific organic coatings that have their own unique properties. Understanding how zinc nickel, performs in those systems situations, I think, is going to be key.
Okay, thank you, Tom. Craig, additional research or engineering needs that you see to better implement these technologies to replace cadmium?
I think Tom hit the nail on the head. Each weapon system has to look at it, and they have their specific, or I should say, an Air Force weapon system have their specific needs. Some might be more concerned with conductivity. We've looked at some other things. For instance, I didn't mention this, like zinc nickel does well. It doesn't cause cadmium embrittlement on titanium, so that's one of its strengths. But I think each area needs to look at what testing has been completed, do a gap analysis, and determine what additional testing needs to be done so they can get it approved on their system. Whether it's some different type of corrosion test or conductivity test, and determine that and take what's been done here by us and others and determine what additional needs to be done.
Right. Just to add one more example, the nuclear environment has unique requirements that cadmium meets. And as we expand zinc nickel into the nuclear arena, we're going to have to definitely do some more work.
Okay, thank you. And Randy, anything else to add to that in terms of research?
I think for the most part, Tom and Craig both agree with everything they said. A lot of it is going to be, as we go forward, it's understanding the requirements, and we don't always have a lot of background in the history of why we're using what we're using. We just know what the performance properties of it are, but are there any underlying reasons or anything that we don't know? And then I think everybody can pretty much agree that somewhere down the road we're going to find things that were CAD plated that we had no idea were. We have things like this that are pervasive, and we know most of the top level applications, but there's always those oddball things that pop up that nobody thought about before, and we're just going to have to address them as they come up.
Okay, thank you. And with that, on behalf of CERTIP and ESTCP, we would like to thank all three of our speakers today for their excellent presentations and this discussion as well. The next webinar in the CERTIP and ESTCP series is on Thursday, September 7th. It's titled Research and Development Needs for Management of DoD's PFAS Contaminated Sites. This webinar will feature three presenters: Ms. Maureen Sullivan, who is the Deputy Assistant Secretary of Defense for Environment, Safety, and Occupational Health, Dr. Andrea Leeson from CERTIP and ESTCP, and Dr. David Sedlak from UC Berkeley. Registration is open for this webinar, so please visit the Startup and ESTCP webinar webpage to register for this and other future webinars. Before we conclude, I would like to remind you that both the audio and a copy of the presentation of today's session will be archived on the webinar webpage in case you would like to refer to them in the future. We would appreciate it if you could please take a moment to complete the survey that will pop up on your screen at this time. Thank you.